Hello, everyone. Last day of the week. We postponed, Monday to today. We had conflict of schedules on Monday. That's why we postponed it till today. So we still try to do 4 days a week. Same time, same station. And what's the deal? Well, we started the week with the Slit Experiment.
Wait, the 4 days are, to be clear, Sunday, Monday, Tuesday, Wednesday, right?
Yeah, Sunday through Wednesday, and sometimes we're going to switch a day over to Thursday. For us, it's not important what day it is, but we're just trying to give at least 4 presentations per week. And part of that is because we got other activities or we want to spend the time on other things, and they really take up so much time that we couldn't hold on with 5 days. It was just too much. So we're going to try it from now on with 4 days, okay?
We're finding the right...
we're
start
still
off with 1, then we went over to 5.
We're still trying to adjust our schedule to find out what fits better, what is more efficient, I guess.
I also think we're getting better at doing these podcasts in general. We started off more choppy, more amateur. We're getting better at it.
Yeah, that's one thing. The other thing is, we do a lot of improvisation here. All of it is improvisation, essentially. I do have some gifts that I usually put up there so as to make the presentation a little more visualizable, that we can see something. We can, pictures worth 1,000 words, that kind of thing. But in general, the discussions I have with my son here with Ans are just improvised completely.
But we're getting better at improvising.
Are we?
We're getting better at conveying our thoughts. Because, when we talk in the kitchen, we do talk different than how we talk here. Because we kind of understand, we're on the same wavelength.
But we end up with black eyes in the kitchen.
Yeah, but when we're doing it here, we kind of have to talk to each other in a way that a third party can understand.
Yeah, and again, we're doing a lot of brainstorming out loud. We're improvising a lot of stuff here, and I think that's good because it allows us to look at things in a different way. Sometimes I learn something new. My son is a good sparring partner for this kind of thing. Anyways, we started the week with Slit Experiment, more or less. We're looking at the properties of light. And I continued with Compton scattering, Compton Effect. And today I just like to cover a little bit of the Photoelectric Effect, which is pretty much like the Compton Effect, except that it doesn't look at what happens to light. It just looks at what happens to electricity itself. The fact that light stimulates electricity, and that's essentially it. Well, let me review again very quickly. We're going to do, here's the Slit Experiment. This is what I did. I had a needle in a cork, and when I shone it against the screen, all I did was, let's see if I can find it here. All I did was point a laser pointer at a needle stuck to a pin. And let me show that real quick here. That's what I did. Needle, okay? And here's the laser pointer. I pointed it out there, and at the wall, and this was a red laser pointer. And you can see the fringes that I took a picture of it here, and you can do the experiment at home, always in the presence of a trained relativist, hopefully, so that you don't get hurt. And you will see those same fringes, and you can see the little lines there separating the little red dots there, and those are the fringes.
Does that laser pointer work?
No, it doesn't. Not anymore. So you see the fringes, and we did it with a laser point. I did it with a needle. In other words, I don't need a slit, and we don't need to go out there and measure how thick the slit is, and do all those kinds of things. This is a much simpler experiment. You do it just with a needle, and you're done.
They cheated. This is a slit right there.
No, yeah, but I did it on the thick part.
Oh,
yeah.
you do? Oh,
Yeah,
okay,
just
okay.
in case, because people might wonder about that.
Yeah, because it was the needle, but it was
yeah.
the other side of the
See,
needle.
the needle, let's see if I can point it here in the right place on the camera.
Well, no, just people know what a needle looks like.
Well,
the pointy end is in the cork. So
yeah,
so the other end is where the string goes through. So there is a slit there.
Yeah, but that's not what I used.
That's not where he shined it in the middle.
Yeah, what I shined it right there, right. I shined it in the middle, so you can put a pin there if you want. Not a needle, you can put a pin.
Or a hair.
Or a hair, human hair. It'll work with anything that's very thin, and it'll break the beam, okay? And what you will have is these fringes on the wall, okay? That's what you'll observe, something similar to that. And all we're saying here is that you don't need a slit. You don't need two slits. And again, the two slits is very confusing. And the reason it's confusing, people think that, maybe the little photon balls, energy balls, wave packets are hitting against the frame of the window, of each of the slits.
Do you have a picture of the slits so they can be...
Not at the moment. I don't think I did. No. No, I don't have one right at the moment. But just imagine,
two
again.
windows next to each other.
In fact, this one is kind of like that.
You know? But you can't see that. It's
yeah.
like two windows next to each other.
Right.
And the slit is essentially the frame in between them.
Right.
That's where you're aiming the thing, and the confusion with the photons being discrete balls is that they can bounce off of the edges, the outer edges of the window,
of the frame,
of the window frames. Yeah.
Right, and what we're saying here, you don't need those edges of the window frame. You can just put a needle, and now there's nothing to bounce against. And if you're still producing, fringes, then there's got to be a different explanation for the. Especially, you got to use a different model for light. You can't use particles because the particles should go straight ahead. And I showed a picture of that last week. Here I'm just trying to summarize. I'm just going to say that this is my version of it. The ropes from every atom in the universe are interconnected. We start with that assumption. And we're saying that the atoms that form the laser pointer or whatever light source you use are already connected to the atoms of the needle before you start the experiment. Every atom is connected to every other atom with ropes, with electromagnetic ropes. And those same atoms from the needle are connected to every atom that comprises the screen, or whatever you use as a background, wherever you're going to project the light onto. And as you turn on the light, which is what I'm showing there, you go from this darkish to that point there, and you turn on the light. And once you turn on the light, all you're doing is stimulating the frequency on the ropes. You're increasing the frequency, the torsions on the ropes increases, and the link lengths are shorter. And by doing so, it comes into the visible spectrum of light. Now you are able to see light. Okay, you turn on your laser pointer, higher frequency, shorter wavelength, and that signal is transmitted to the atoms that form the needle first, and from there relayed onto the screen. And of course, then it's a straightforward wave thing, nothing invented here. It's they're in phase, you get constructive interference, and if they're out of phase, you get destructive interference. Destructive gives you a dark band, constructive gives you a light band. And that's it. That's how simple this experiment is. We do have a quick solution to a problem that has stumped quantum mechanics it's still stumping them. They're still using the assumption that a particle can be at two places at once. They're using the uncertainty principle to try to explain it. Which says, again, that you can't tell the momentum and location, position of a particle simultaneously, and that kind of thing. So they get into all this word wizardry and magic in order to explain it. And here we have a very simple explanation. We're just saying, look, you get constructive interference. What does that mean? That means that the ropes coming out of the same source are off by a quarter wavelength, half a wavelength, whatever. And that's where you produce the dark and bright fringes.
To clarify, the constructive interference and destructive interference, where is it? Which two ropes are we talking about that are off angle?
Yeah, it's important to know that we're talking about the same ropes. In other words, let's clarify that. One atom, just any atom at random from the source, that atom is connected to two atoms on the sides of the needle. Okay? So we have one atom. Let's see if I have it here. I think I have it more or less here. So it's good to talk with something. There you see it. You see two atoms around the needle. And just think of one atom. Oh, there it is. One atom just connected to two atoms. You see that?
Yeah.
One atom in the source of light connected to two atoms on the needle, one on each side of the needle.
Okay.
Now that same atom, we're just looking at one atom here, okay?
And
one atom from the source. I'm sorry, and two atoms from the needle.
Yeah.
If you look at that now look at the following graph here, and you'll see that the lines connecting the two atoms from the needle to the screen have different angles. In other words, there's a different distance from one atom of the needle to the screen compared to the other atom of the screen. So they have different lengths. You look at each one of those lines.
It's hard to say because I'm not seeing what you're seeing.
Well, the yellow lines that you see in a second, you'll see all these yellow lines. Okay, all these yellow lines. You can see that they're offset. The two atoms. They come from different angles to the screen. The lines that connect the atoms to the screen are at different lengths. And so they are obviously at different, they're at different angles. That means that they're going to be off at some point by a quarter wavelength, a half a wavelength, and so on. And at other places, they're going to coincide. Where they coincide, we have the bright bands, and where they don't coincide, that's where we have the destructive interference.
You mean the two? Let's just take one atom on the wall.
Okay, the one on the left.
Yeah. Okay.
Completely the one on the left. Okay.
We're talking about the two ropes that are from the needle
to
edges
to the atom.
To the atom. That's
right.
So it's
you'll see it there.
Source,
you'll see how far
ropes,
the two lines are.
Source two ropes to the needle edges, and needle edges two ropes to the furthest left one. For example.
Correct. For example.
The one on the atom on the left side of the needle is closer, and the one on the right side of the needle is further.
Correct.
Just for clarification.
Correct.
So with that angle difference, you're gonna get some distortion in how they touch that atom.
Correct.
But we're not talking when we see the wall. We're talking about the rope between the atom on the wall and my eye, aren't we?
Correct. Very correct.
So where is the relation between how the two ropes from the needle edges come into the wall to give me the signal in my eye that there's either a line there or not a line there?
Unfortunately, I didn't illustrate it here, but I do have that illustration in my website. For anyone who wants to see it, look up the Slit Experiment in my website, and you'll see the illustration of what Hans here has just described. What he's saying is the following. If you look at just the yellow there, the two atoms connected to the far left, they're off as far as the length of the distance from those two atoms on the needles to that farthest of all atom on the left, right? So they're offset. Now the question is, we are looking at that same screen, and we are getting a reflection, or we're getting a signal into our eye. And so the question is, why do we see fringes? Why does our eye see fringes?
Well, I guess the correct phrasing is, why does that atom on the wall reflect?
Yeah.
What
a dark band or a light band or whatever.
Let's say a dark band.
Okay, a dark band. Okay. And what I'm saying is the following. First the needles the atoms on the needles are offset by, let's say, half a wavelength, okay? And that allows us, that triggers a dark band there on the wall. Why? Because it's a lower frequency, because they're not stimulating each other. You see, if they coincide, then they stimulate the atom. But if they don't coincide, they don't. One stimulates the other one destimulates it, kind of
but
thing.
To clarify
okay?
that, if there were only one atom, if there was only one rope to the wall, would we see it? So we would see if there's one rope to the wall, but we can't see it because there's two ropes to the wall. This destructing the.
Correct.
But that's a weird notion that if I shine, you're essentially saying if I shine one rope light on the wall, it's fine. But if I shine another rope light on that same atom with a slight torque
coming from the same light source,
the same light source, then all of a sudden you can't see that light.
Yeah, because what's happening is it's kind of like one canceling out the other. It's a very, remember, this is a very sensitive experiment, in the sense that if they're off by half a wavelength, you're gonna one is gonna stimulate the atom, is gonna try to give it this higher frequency, but the other one is gonna lower the frequency because it's kind of taking away. Remember, the atoms also give back and forth, so the atom on the screen is also giving a feedback, right, to the atoms, to the two atoms on the needles. But I just want to concentrate on what you see now. Okay. There's a rope. At least one rope. We'll just talk about one atom on the screen and one atom in your eye, right? We're just going to look at one atom and one atom. What happens? If that vibration of the atom on the screen is low, so low that it goes below the visible range, we can say it's a dark band, or it's just, again, below the visible range, then at that point, that's the signal that's going to be sent to your eye, and it's going to be below your visible range. The one next to it, or a few rows down, whatever, that's a bright band because they both coincide. So that's a shiny atom. It's vibrating at a higher frequency, and that one's going to emit to your eye a shiny, a higher frequency, and you're going to be able to see it. Since we have this ability to see, across the whole screen, almost, simultaneously, all of them are sending signals along the ropes connected to each one of the atoms that form our eyes, or the sensors in our eye, then you're going to see the dark bands coming, low frequency coming from all those atoms that have low frequency on the screen, because that's what they were sent. That's the signal they were sent from the needle. You're going to have the bright ones coming from the bright bands, because that's the signal that the needle sent to those atoms. So you're going to have the vibrations of the dark bands will be lower. You're going to have lower frequency. It's below the visible range. You can say it's a dark shadow, and the other ones will be bright, and that's the signal that you will be receiving. And I think this does explain. Unfortunately, I didn't bring that, but that would have been nice to show, because I do have a picture of that, of what the observer sees. We have the slit experiment there, and then the light coming to the observer's eyes, and I'm showing that's what the observer sees, because that's the light band from one area and dark band from another one.
If we put like a more accurate than an eyeball sensor on the wall,
right,
you would still get some form of reading between the visible lines.
No doubt about it. If you put a photosensitometer, that's what they're called. If you put a photosensitometer that has the ability to look at intensity, light intensity, and you put one right next to the other, one right where there's going to be fringes. Mm-hmm. So instead of having a screen, you just put a series of photosensitometers for each one of them. Or at least the main points. You don't even need to have a whole row of them. You can have one at the edge, one in the middle, one at the other edge, where there's going to be a dark band. Mm-hmm. If you put a photosensitometer there, you're going to see the intensity drop where the dark band is, and be high where the other one is.
But it's gradually. It's like the more the two rope angles coincide, the more it becomes a focused line,
and that's what you see. So by the way,
blurs out,
and that's what you see. They are blurred out. They're not complete. See, if you look look at this. I want you to look at the picture here. because the picture,
Yeah.
no, where is it? This
I
one,
remember
fringes.
it.
This one, if you can see, there's a halo. There's a smoke around each one of
But
them.
then I
It's
think
not
it's-
clear cut. It's like
Yeah.
like vanishing and then coming back out.
But I think then it's incorrect what we said yesterday
Uh-huh.
about sucking out the air would make it crisper. Well, no, I guess it would make it crisper. But the way I imagined it is, if you sucked out all the air, essentially took out all the variables, you'd get these perfect lines. But you're saying no matter what, you're gonna have these essential.
I think you're going to get them
gradients.
anyways, because even if you remove the air, which is the experiment I'm suggesting to do the slit in a vacuum, that's what I call it, the slit in a vacuum. You remove the air, that would help give us an idea what would happen if if other factors in the room where you carry out this experiment are removed. And I think
Removing
one of them
variables.
is the air. I'm sure that
It's
if you
removing variables.
yeah, it's removing other variables, what Bohm called hidden variables.
But I had this notion that if you accounted for all the variables, if you removed everything else,
Uh-huh.
and you did the slit experiment in a vacuum with whatever temperature is necessary, you'd get this exact stripe pattern. But you're saying, since the angles kind of gradually focus and go out of focus, if you kind of see all the atoms in sequence,
Yeah.
you'll see that there's a maximal focal point where the two ropes from the edges of the needle touch the atom at the exact way they need to. Essentially, they blend perfectly.
Correct.
To reflect the light. I'm guessing 100%.
Yeah.
Back to
We'll
your
call it
eye.
out current.
While the
yeah.
one right next to that is like 99% accurate, then 98.
And you can see it here.
So my point is, no matter what, you would have this blur essentially.
Yeah, because look at this. You got a 360-degree circle made by the two ropes. Just think of it that way, right? And and from atom to atom, one right next to the other, and we're talking about a very, very fine scale. We're talking about angstroms here, right? There's going to be a twirl just a little bit, one from the other, and so, all these angles will be one atom right next to the other, right? You're going to see this whole circle. So it's got to be a gradient and coming back out. And I don't think by removing the air, you're not going to change that. So
that was my point. I thought you get this crisp lasers. But
I think you're still going to get it crisper,
Yeah,
but not
crisp.
crispy, completely crispy.
I've noticed there's a lot of angle talk also when we're talking about gravity, according to the rope hypothesis.
Yeah.
They seem to be similar in that aspect, where you're essentially comparing angles.
Yeah.
Angles
You have to
make
remember
a lot
one thing also. Keep that in mind that, the measurement of the speed of light today is done with angles. It's calculated. It's not measured.
I don't think you can measure it.
Yeah, you can. It's not measured. It's calculated, and it's also calculated on the basis of reflection. A lot of people criticize that because they say, we never get to measure the speed of light one way. It's like they use all these fancy things because of the distances involved and the time involved, the fact that light is so fast, that you have to kind of fool Mother Nature or light, whatever, to try to see if you can measure it. And you can't, and you measure it to some degree, but the final thing is done with calculations. You need to put it into an equation to calculate the speed of light, and that's how they do it. It's not like, you calculate, in order to really get the speed of light, like measure in one direction, you kind of have to throw it, from here onto the moon or farther away. Then you got a one-way. But otherwise, you get a two-way reflection, mirrors, calculations. You get a lot of stuff like that, and people kind of wonder about that. Why we can't get it in one shot? And as far as I know, I don't think anybody's measured light one way. It's always two-way reflection, calculation, and angles.
I just like how important angles play when we're talking about light and when we're talking about gravity. It seems to be like Mother Nature seems to like angles.
No, we like angles because light always travels straight. Why straight? Because the rope is straight. It's taut.
But so does gravity.
Yeah, but then that gives you an idea that we're dealing with something that is completely straight. it gives you a clue on the nature of light.
That's gonna be my next question. Does gravity travel straight?
Well, objects travel straight towards the center of the other object, but again.
We were talking about the Slit Experiment.
Yeah, but anyways,
let's not go too far off.
No. But angles are important because, and again, I think we can do angles with light and with gravity because they're mediated by ropes, and the ropes are taut. Mm-hmm. And so, at our level, the rope can be considered a one-dimensional line.
Let's not go there.
No, but essentially you can treat it as a one-dimensional line for our purposes of the macro world because we don't have anything as thin as the electromagnetic rope. So for us, that's even sharper than a pencil. It's or any string or any wire that you can make. You're talking about light. Anything we can make is made out of atoms, and light is
a fraction of an atom.
A fraction of the thinness of an atom. So there's no way we can manufacture a wire that is as thin as light.
Wait,
Keep that in mind. That's important.
I got an equation for you right now.
An equation?
I know the size of light compared to an atom.
Okay.
Is the fraction. Oh man, how do you say that? Because talking about a hydrogen atom for now.
Yeah.
You got a hydrogen atom.
It's about 3 angstroms wide.
The ropes coming out of that atom, which comprise the atom, which essentially is the whole atom, the amount of ropes is the amount of other atoms in the universe. So there's your fraction of the difference between a hydrogen atom and the size of light.
Yeah.
That's my equation.
Okay, yeah.
Can I get my Nobel now?
Okay, that's a conceptual issue, yeah. You have to prove it.
I did, because I just gave you an equation.
No, I don't,
Equation's proved. But yeah, light, compared to a hydrogen atom, light is the fraction of the fraction.
One atom divided by the number of atoms in the universe?
Yeah, that's the size of light compared to hydrogen atom.
Yeah, then you have the fine structure constant, that kind of thing. That maybe that's the number, but that seems a little too wide for what light is.
But that just shows you the how
thin it is. Yeah, I like to say it's thin.
I mean,
very thin.
When you the fraction is literally 1 over the number of atoms in the universe.
Yeah, imagine for us,
fraction.
We look at a spider's web and we say, "Oh man, that's thin." Each one of those little lines that the spider makes, that's immensely thicker than what light is. So we can't even wrap our brains around how thin that thread has to be, or the rope has to be. It's very, very, very thin. You cannot. It's almost unimaginably thin, and that's important because if you're going to go with a rope model, you have to factor that in. That you're not dealing with anything that we know of in the macro world. Any wire, anything that you can see, is infinitely many times thicker than the rope model, than the rope that connects 2 atoms. So we're talking about something extremely thin.
To get back to what we were talking about, constructive and destructive interference.
Yeah,
and
here I have it.
We were talking about the Slit Experiment before that.
Yeah, so we have
I kind of cut you off with that.
No, it's fine. Here we have the constructive interference on the left and destructive on the right. What does it mean? That they're not in phase, and when they're offset like that, that's what you're going to get. And again, this comes from wave theory, and there's nothing wrong with it at all. I think it's perfectly clear that that's what's happening also with the rope. Nothing to modify there at all. Okay, but moving on, we have the other issue that we went into what Compton did, and that's we looked at his atom. His atom was the Bohr, Rutherford-Bohr model of the atom, which is a planetary model. They don't like to say that it's planetary, but it is a planetary model. They deny it only, not because it's not what you see there, because see over there you see the little planets orbiting the nucleus in a very irregular way, And the only objection they have against that is not the planetary model. What they have an objection there is that the electron does not orbit like that. The electron essentially jumps around within the orbital, right? It jumps around the orbit. It could be anywhere around the orbital. That's the only question they have. So they're saying it's not a planetary model in the sense that the Earth orbits the sun in a regular, predictable manner, but instead the electron jumps around. It's unpredictable, and that's where the uncertainty principle comes in. Werner von Heisenberg, he said, look, we can't tell you the position and the momentum of the particle of the electron at the same time. When we know one, we know less about the other, and vice versa. And that's the only issue. But other than that, what you have is a nucleus, or you have a star like a sun, and you have a planet. The planet is the electron. The fact that we don't know where it is in the orbit is irrelevant. We still have, from a conceptual point of view, a sun and a planet. And in that sense, it is a planetary model, and not in the sense that it orbits regularly.
Yeah,
that's the only thing we have to clarify that. Okay,
it's like I guess it's inaccurate to call it a planetary model in that sense, because it's a bowling ball with a ping pong ball.
Correct, and we don't get away from that.
It's just that ping pong ball isn't going around; it's just teleporting along an itinerary.
Yeah, it's jumping around. It's jumping around.
It's jumping around along an oval, but not predictably. It's just like it happens to be here on that orbital. Yeah. And then here, then here, then there, and there.
Which they can't explain anyways, by the way, because I mean, why would the electron do that kind of magic? And again, if it's teleporting, it's violating the speed of light, because it means. When it's on one side of the orbital and then suddenly on the other side, it beat the speed of light by getting there. It did it through magic. And again, there's no justification for that model either, for either of the two models.
Or why it doesn't fly away.
Yeah,
or why it doesn't come closer.
Right, what are those rings? Like you see there, what are those rings?
What's the itineraries
where
they can be found.
Yeah, but what I like about them is that they turn the itineraries. I mean, they could have gotten rid of the rings and just shown the electron, but then you wouldn't see the regularity. And so what they do, they leave the rings so that you can see the itinerary. And so people have gotten this idea that is exactly the model, and that is a planetary model, and that's the one that quantum denies and say, well, no, it's not accurate. Why isn't it accurate? Is it because the electron is not a bead, because the proton is not a ball? No, that's not the issue. The issue is that the electron can be anywhere around that orbital.
I mean, this is the symbol of an atom is literally what you're showing here. It's a ball with a ring bead. With 3 orbitals, or 4 sometimes, with a bead on that. Oh, I mean, that's the popularized symbol of an atom. Yeah. So, is it or is it not an atom?
Right.
What are we talking about here?
And again, those rings, those hula hoops, don't exist. First of all, second, even if the electron jumps around, you can't justify that model, so it doesn't matter. You can still call it the planetary model, not because it orbits in a regular manner, but because it involves 2 objects, a sun and a planet, a star and a planet. In that sense, it's a planetary model.
Or a bowling ball and a ping pong ball.
So that's their starting point, and that's the starting point for Mr. Compton. He starts with that. And then the issue is, what is light? Is light a flow of ping pong balls, of rocks, or whatever you want to call them, discrete particles, or is it a wave? And, the other problem that what you see there, those two are irreconcilable. You cannot reconcile the flow of particles with a wave. And they can't either. The mechanics, they can't reconcile them. What they did here is they went in and they created the principle of complementarity, and they said, look, light is both. And the way they showed it is that through experiments, they say, look, when you have a bundle of energy, a packet of energy, we're going to consider it as a ball because it's discrete. And that was shown by Max Planck in 1900. And then when we have to explain, the experiment, like in fact the Compton experiment, you explain it in terms of wavelength and or frequency or whatever. In other words, wave properties. And you say, how can you reconcile the particle, the packet, the energy bundle with an extended wave? And you can't. Obviously, one thing has nothing to do with the other.
What was the experiment that makes light a packet? We talked about many of the.
Okay, that was the black body radiation that Max Planck calculated. It's a calculation. Essentially, they're saying that energy comes in discrete packages. Okay, that's the bottom line on that. And Einstein used it in 1905 to explain one of the things I want to talk about today, which is the photoelectric effect. Photoelectric effect was discovered by what's his name, Hertz, Heinrich Hertz. I think it was 1884, and he discovered that when he shines a light on a polished metal surface, a current flows. And that was surprising. And it wasn't until 1905 that Einstein explains it using Max Planck's quantum that he had discovered 5 years earlier. And Einstein uses the little h there, the variable that Max Planck came up with, which is the quantum variable. That h with a little broken leg there. That's the one that they use for the quantum, and that's the energy content of a photon. And the issue is that that comes in discrete packages. It doesn't come continuous. It doesn't come like a flow. It comes in chopped pieces.
How do they know that? Or how was that?
It was just, again, it's an equation. It's got to do with equations and nothing else.
But is it really equations? Because I can imagine that being observed when you shine a light on a polished metal surface. Assuming it's this, what did you call it earlier? A photometer?
Photosensitometer.
Photosensitometer. I'm assuming you get this like blips and not a continuous like boo or whatever. I don't know what.
What they're saying,
you get like a heartbeat essentially.
When you look at the graph, what you get is jumps.
Yeah, but that's what I'm saying. So
and those
it has
jumps
been observed, not calculated in that sense.
Well, yeah, it's observed in that sense, in the fact that you get it chopped off in that sense.
We're detecting.
Yeah, and in order to describe that, that's where Max Planck came up with his equation, showing that each chopping of those histograms, because you think of it as a histogram, each one of those comes as a histogram, comes with a fixed energy content.
Yeah.
And so they said, look, whether you like it or not, it defeats all of our intuition, our common sense, because we always thought that light comes in a continuous flow, and these guys are saying no, it comes in packages. It comes in in flows of bundles of energy.
It's continuous blips.
Yeah, continuous blip, correct.
Incessant blips, which would be the right word.
Which is the upper, what you see there on the upper side, which if you look at that, those are the photons moving across, right? Mm-hmm. And what we're seeing there is essentially what Planck, Einstein, and later Compton, 20 years later, they came up with this. They said, it comes in discrete packages. But what's the issue? And here I try to illustrate for today what Compton essentially discovered, and this is it. What you have is light coming in, hitting an electron. By the way, the electron is a little ball, and the electron has to stand still because he uses the rest mass of the electron. And when it does so, when light hits it, as you can see, they're all coming as balls. The light is the yellow coming from the left there. And all these electron balls are hitting the electron out of there, the photon balls, I'm sorry. And and there is a deviation of the beam of light. And that light comes at a lower frequency than the one coming in. So if you shine X-ray frequency onto an electron ball, the ball goes out and absorbs some of that energy, and what's left, what's ricocheted, is the photon going south in there in this example, and it's got lower frequency, longer wavelength. That's his explanation. And in other words, what he was able to produce an equation that described this, and that's where he got his Nobel Prize. Okay. Now, what do we say? Well, I'm saying that the rope model is, and it took me a little bit today. I almost didn't have it ready for today, but fortunately I was able to. Oh no, that's the wrong one. Sorry. Let's get the right one in there. Where is mine? Oh, here it is. Okay. This is my version. Okay, this is the rope version. And what we have here, and again, you have high frequency rope. Okay, that's the X-ray coming in from the left. The stimulus that it gives the atoms compels them to twirl the entire row of atoms or molecules. It could be, I simulated this with nitrogen atoms. You have the S, what do you call it? The S,
S shell?
The S shell, encapsulating the three P shells there. Okay, so I just did this with with nitrogen atoms. Essentially, what you have from the left is a rope that, with high frequency, it stimulates the atoms to twirl. That's going to be electricity going rightwards, eastwards. And south, what you have is a lower frequency, longer links, and slower twirling of the rope, essentially, and that's lower frequency. So you have longer link lengths and lower frequency compared to the higher frequency, shorter link lengths that are coming in from the left, which is the X-ray source. Okay, so that's the Compton version, the Compton model, the rope version of the Compton model. That's what we have.
Well, I guess the rope explanation for the Compton experiment.
Uh-huh.
I have a question about the, what do you call that? You have it, let's just talk about the first one, right? The first atom.
Okay.
Is twirling or spinning.
Yeah.
What do you call it? Perpendicular, I guess, to the first one. The light, the high frequency rope going in, it's spinning.
At the same on the same axis.
Yeah, I guess you could say that.
Not necessarily. Remember, a lot of this, I think, has to do with the refractive angle. When you put a pencil in the water, it breaks. The water breaks the light, and you see it like a broken pencil. Mm-hmm. And so you say, well, why does light do that? Why does light break the pencil? Why doesn't it make it, twirl or do something the same direction in which light is coming? And again, there's a refractive angle. And I think that this, here I show it on the same axis, but I don't think it occurs on the same axis. I think there's a refractive angle. And if we probably looked at Arthur Compton's experiment here, you would have more like a fork where the light, the X-ray source coming in, kind of forks like a Y. I think that would be more accurate to show what Compton saw. It's got to be more like a Y. I'd have to research that to make sure that that's the case. But I would suspect that there's going to be a refractive there's some angle between the light coming in and the electricity coming out on one direction and light coming out in the other direction.
The direction in which the atoms spin, they don't always spin along the same axis that the
correct
high frequencies.
That's the first one. The second one is light is scattered. Remember, light, all the ropes coming out of those atoms, or at least out of one atom, right? If you choose one atom, all the ropes coming out of that one atom that's being hit,
Yeah.
I think they go in. They do go, and it's not that I think they do go in every direction because they're going to other atoms in the universe, especially those in the vicinity. And so light gets scattered along each one of those ropes at different frequencies, different wavelengths, and that's what Compton essentially discovered. He showed that there's a relationship between the angle and the energy content. In other words, the wavelength.
Where the high frequency comes in, and first and the two angles at which the well, what do you call it? The angle at which the atoms spin, and the angle at which the relay of frequency goes out
Along each one of the ropes, right?
Each one. I'm guessing with one being the focal point or the hot spot. With
Yeah,
the
right. And from there on, everything is declining, like in wavelength, and in other words, increasing in wavelength and decreasing in frequency.
My question was, I mean, it might derail the topic, but it just springs to mind. When the atom's spinning, for example, here you show the atom spinning. What do you call it? You could say
clockwise,
it's spinning like a wheel away from us, right?
Okay.
That's kind of what you were going for.
Yeah.
So now my concern is any ropes, for example, the high, the low frequency one coming out the bottom.
Yeah.
Is what do you call it? It's on the outside of the wheel. So you got a spinning wheel.
Yeah.
And this rope is coming out, not on the axis of the wheel, but the rubber of the wheel, essentially.
Yeah.
How does it stay in place with this atom spinning?
Well, there's
I know a big explanation. That's why I don't want to go into it. But
no.
What comes to mind.
It is a valid question. I mean, the question is, does the electron shell cut across ropes?
Because essentially, you're showing here the atom spinning and the rope staying in place.
Yeah, and that's something you got to answer under the rope model. And the question is what is actually spinning? Are we cutting across the ropes here or not? Is there friction at the point where the rope meets the atom? All those are valid questions, and it's not easy to visualize for sure, and we have to admit that much.
This could also be a question for another day.
Yeah. This question is quite complex because it's got to do with whether ropes cut across ropes, threads cut across threads.
It goes into the ropes going through ropes.
But it's a question you have to answer, and again, you have to think of something along these lines, just as food for thought. The rope, the way I look at this happening in real life out there, the way Mother Nature does her tricks, is that, when an atom moves, it moves like a ball along a bead on an abacus. So it doesn't necessarily have to cut across in that sense, not always. Another way of looking at it is, when you shine a flashlight against the wall and you move the flashlight real quickly downwards, it's not like you're moving the ropes downwards. What you're doing is stimulating different ropes, and so that could fool anyone, right? And this is something similar. When we say that the atom rotates, spins, remember it's pumping, right? And it shakes and it also spins. So it does all these motions at once, and that's very hard to visualize because you kind of have to treat these things separately. You say, if it vibrates here, I can understand. If it pumps here, I can understand. But it can, and when it rotates or spins, I can understand that. But how do you do all three simultaneously? That's very hard to visualize.
Here's a more specific question that I want to clarify. I feel like a reporter, hard-hitting reporter. I want to get to the bottom of this, Mr. Gady. When you talk about electric current, you always mention the electron shell spinning. You don't talk about the atom spinning.
But the atom
is there a difference?
I don't know. Does the little star, the proton star, spin itself? I would think it does. I would think the proton. I don't think anything is static inside an atom. Nothing. But then the other issue is whether they synchronize. In other words, are they spinning all as one block, or is one spinning inside the other?
For more complex atoms, you mean?
No. For any atom,
For
let's take the hydrogen.
hydrogen
Let's take
atom.
the hydrogen atom. Let's go simple because
Okay.
this is complex as it is for a hydrogen atom.
Which,
Is the
which
star?
two components are synchronizing?
Well, what I'm
That's
saying
what-
is you have the electron shell on the outside and you have the star on the inside,
Yeah.
right? Suppose the electron, the proton dandelion, as I call it, the star, is made of one thread coming from the rope, just one. The other one
Yeah.
goes around and forms the electron shell, right?
Yeah.
And the question is, do they break at that point, and does it become a separate entity, the proton, and begin to spin inside the electron shell at a different speed and with different ideas than the electron shell? Is the electron shell spinning in opposite direction? These kinds of.
The hardest part to imagine that is a spinning object without entangling, because the spinning isn't it. Because since the ropes or threads in this case go through each other, it's hard to imagine a spinning ball of yarn that isn't entangling. That's the hardest thing to imagine here.
Okay, but now let's assume it's not spinning in the sense we understand spin. In fact, quantum has that same problem. When they talk about spin, everybody thinks, oh yeah, I know what spin is. That's not what quantum understands as spin. Whatever you understand spin, the top spinning,
Yeah.
that's not what quantum. Spin is orientation.
Okay.
They'd call that the spin of the electron.
Orientation with respect to what?
Let's. Is this oriented that way, right? This way, that way?
Okay.
So they're saying, don't think of this as something that's spinning.
Okay.
The word spin, everybody understands what spin is, a top spinning. That's not what quantum understands what spin. It's the electron has been found at this orientation. We'll call it, that's spin one.
Okay.
This is spin two. This is minus half
Yeah.
spin. What's minus half spin? It
That's
means
what they
it's
call
it's
it?
point. Yeah,
I thought
minus
you pulled
half.
that out of your.
No. They call it. I didn't invent this
That
stuff.
sounds
Minus-
like you just came up with that on the minus half spin.
It's a half spin, a minus half spin. You say, what does that mean? And they say, well, we can't explain it.
Okay.
But then everybody says spin, and everybody says, oh, I know what spin is. No, that's not what spin is in quantum.
Weird thing. These atoms are. It's hard to imagine when you talk about spin. You mean spin, but you also don't mean spin.
Right.
Because
It's a double.
anyone who's trying to imagine this right now, imagine the ball of yarn spinning without entangling.
Right.
How
Now-
do you even imagine? Is
Yeah,
it
but
spinning at all?
now let's imagine that for a second. Let's assume that there is no such thing as spinning of the electron shell.
Okay.
What we have is the vibrations along the surface of the electron. So think of a worm moving along, the surface of the just one. Let's look at one worm only. So it's wiggly
Are you
around.
talking about slack?
No, I'm talking about at the electron shell.
Yeah.
You have it forks out. The rope forks out. One becomes
Yeah.
the electron shell, or forms the electron shell. The other one goes to the center of the proton, right, or the nucleus, right?
Okay.
Okay, so we have one thread going in the center and one going sideways, right? 90 degrees to it and going around, okay? The one going around, I think, is curly. It's a wiggly little worm. It's not a straight one. It's wiggling around.
Oh, okay.
And now imagine it just vibrating.
Wait, real quick. Wiggling in and out, up and down?
Kind of both. I can't tell you exactly which one, but
okay.
just imagine it. It's not a straight one. It's not a. It doesn't go straight across, but it kind of wiggles across, whether up or down or sideways. I don't know. I would think it's sideways, so that it gives this texture to the
Like
electron
thickness.
shell. Yeah, like a thickness, because one goes in, the other one goes out. So imagine gazillions of them. They form this fuzzy ball, right?
Okay.
But what I'm saying here, imagine that, we're thinking about this guy spinning.
Yeah.
And what if that spin is really something else? What if that spin is actually, the vibrations of that worm that's all around the electron shell moving forward? Just and
Like-
so we think, oh, how can it spin? Maybe it's not spinning in the sense of
Okay,
a
I see
top.
what you mean. It's exactly like a worm. When the worm kind of contracts and then pulls forward.
Something along those
Something
lines. The
like that,
motion of that
where-
might not be the spin that we're thinking of.
I mean,
spin.
it's like I think slack is kind of the right way to conceptualize that, because when you have slack, you have something that you can pass around essentially.
Yeah.
So-
And again, I think of this as something that's wiggling, that's not straight. I think it's what's his name? De Broglie. He came up with in 1924. He got his Nobel Prize for that also. And he says, the electron can be thought of as, imagine a rope going around a lasso, right? The electron is a lasso, but it's made of integer waves. In other words, the number of, if you were to count the number of waves around an electron, this is what de Broglie said. He came up with a wave nature. Again, he introduced the wave nature into quantum. And he says, I've got an equation that can describe this. And the equation, that's what he got his Nobel Prize for, is that the number of links, according to rope, but think of it, if you want to think of waves, how the wave is one up and one down, and that's one we'll call that one link, or one wavelength. The number of wavelengths around is always an integer value. There's no half wave.
Okay.
That's what he comes up with. So he says, look, the electron is like a wave, but he thought of it as a particle.
Mm-hmm. Well, that's what you would assume. If it's in integers, you would think it's countable particles, discrete.
Exactly, and that's essentially what he did with his equation. But he says it turns out that because it does. You would think that if they go around, some point you would end up with half a wave or something.
Short end of the wave,
and that's not the case. The electron shell is made of ropes that have integer numbers. Not half, not decimal, integer numbers of wavelengths. That's his equation, and that's a rope.
But coming back to this fuzzy electron shell.
Well, that's what I wanted to.
Oh.
So de Broglie's equation fits the rope perfectly, because now you took these one thread from the rope, and that's the one you're going to use to make the proton. But then the other guy is not straight. It's, according to de Broglie, is still wiggling all around. Mm-hmm. And what I'm saying is that thing is vibrating around the atom, there's forming that shell. And that shell is not really spinning. What we understand is spinning, but it's like, it's vibrating all around.
I think the correct words are the slack is buzzing around.
The slack is buzzing around. That's a good way of putting
it. The slack is spinning.
The slack is moving around. That's the spin. And imagine every thread doing that. And so it's like if this thing is moving around, we're saying, oh, look, it's spinning. No, it's not spinning. It's just that the worm is vibrating all around the electron shell.
That's weird.
So you got to think of it maybe like that, and not as cutting across the ropes.
Yeah, I like that.
And that
sounds way better than that's way
and we
better
can call that spin, but for
geez.
lack of a better word.
I feel bad for the person who's gonna have to model this in 3D. We're out of time.
There's no computer program for this, guys. I'm sorry.
There will be, but that guy's gonna have a hell of a job.
But that's the best we can do here today. We'll see you on Sunday. Bye.
I like that.
Yeah.